All right, Mercury takes a little less than 88 days. Actually, if you look it up in most textbooks, it it takes Mercury about 88 days to go all the way around the sun. And as it does that, of course, it's rotating, but it rotates extremely slowly. All right, so what happens is for every let's say Mercury's right here. For every two times it rotates around the sun, it's spun on its axis a total of three times, and it does that because of the tidal effects between the sun and because Mercury is so close to the sun, it does feel tidal effect, um, and and uh, just like our moon feels the tidal effect from the Earth, and of course the Earth feels the tidal effect from the moon, but that causes the moon to be locked synchronous. It's called synchronous rotation or one-to-one resonance. That is, our moon spins around its axis once for every time it goes around the Earth. Um, all right, and we're going to find this true with other moons that are close to um, their host planets, particularly um, the Jovian system, the Jupiter, I should say, and Saturn as well. There's some of the satellites of Saturn that are so close to Saturn that they're in these resonances. Like a anyhow, some of them are 2-1 resonances. Some are like this 3-2 resonances, things like that. All right, so that is the rotation of Mercury. Um, Again, even though it spins really slowly, it does have a magnetic field that's about 1% the strength of the Earth's magnetic field. Here's the thing about the resonance, of course. Um, they're telling us why it's not locked into a one-to-one resonance. So it actually turns out that Mercury, of all the planets, is very has a more eccentric orbit. It's Kepler, of course, told us that all the planets travel in elliptical orbits, but some of them more than others. And there's a if you haven't had the lab yet on Kepler's first law of planetary motion, which says that planets travel in ellipses, and then you get to see mathematically and graphically what an eccentricity is. Um, once you see that, you can understand how some planets are more eccentric than others. Um, all right. Anyhow, let's see. Tidal forces. The sun slowed its rate. Um, yeah. So Mercury's day. So this is its day. Which, remember, it goes around the sun once every roughly 88 days. So for it to spin around once on its axis, it takes about 176 days, longer than its year. Right. Right. Yeah. So all right. So that's. I'm gonna actually do some videos, and we'll talk about and we'll do this for you know for more than just Mercury, but we'll talk about the surface gravity of Mercury and the surface gravity of Venus and the surface gravity of Mars. I already did one, the density of Mercury. We'll do a density of Venus and also an escape velocity as well. So we'll look at these planets and compare the values that we know on Earth. All right. So remember, like for example, the gravitational acceleration on the surface of the planet Earth is 9.8 meters per second squared. What is it going to be if we put in the numbers for Venus and Mercury and Mars? By the way, they're all a little bit smaller than that of the Earth. All right. So Venus is the closest planet to being the same size as the Earth, so not only is it physically, like its radius is almost the exact same. It's a little smaller than the Earth, but its mass is almost exactly the same as the Earth. And yet they have incredibly different surfaces and incredibly different atmospheres. So, you might say, okay, well, you have these two planets, they're relatively close in size and close in mass. How is it that they could have completely different atmospheres and their surfaces are very different? All right, so let's explore that. Okay, so one of the things, Venus is very, very bright in the night sky, and the reason that it's so bright is that most of the light is reflected off of it, because it's very, very thick clouds. You can't actually see the surface of Venus. I mean, like, for example, when you look at Mars, you can definitely see the polar ice caps on Mars. It's very easy. Even a small telescope, you can see the polar ice caps on Mars. But you can see no surface features on Venus. You just see the cloud tops because the clouds are so incredibly thick. And they're made mostly of carbon dioxide. There's a little bit of nitrogen in there and small amounts of water. And there's also, of course, we mentioned this before, sulfuric acid, which is particularly nasty to electronics. All right, so yeah. All right, so and the other thing is the atmospheric pressure is much higher on Venus. It's like 90 atmospheres. Like, if you're on the ground, you're sitting at 1 atmosphere of pressure. About 90. If you were to dive about 90, I know I said this already, but I just want to repeat it. If you were to dive about 90 meters underneath the ocean, you would have the atmospheric pressure that you'd experience on Venus. So, just to give you a sense. All right, so there's the sulfuric acid. The clouds are extremely high. But by the way, let me put this to rest, because I know a few years ago there was a lot of talk, and it might still be out there on the internet. I mean, it's almost always there on the internet. But there was a lot of talk about the possibility of life in the clouds of Venus, because what we detected a molecule that that is a byproduct of living organisms here on Earth, and it turns out that it was not. It was not living things. The molecule could be explained with some of the chemistry that goes on in Venus's atmosphere. So some people, some chemists got together and worked out the fact that, given the conditions on Venus, you could easily show that and of course the presence of the different gases, like sulfuric acid, the sulfuric acid, carbon dioxide, a little bit of water, that you could get this molecule out. I forget, it began with a D. I can't remember what the molecule was, but anyhow, nowadays it doesn't really matter, because that has been laid to bed, and no one is now searching for life on. I mean, of course, there's always going to be people who are like, "Oh yeah, no, that's true. There's life on Venus." I mean, it was, for a little while, it was a possibility because of this detection of this molecule. But when we could explain the molecule in other ways, nobody is proposing that anymore. At least nobody, not any of the credible people in the scientific community. All right. Anyhow, let's see. Sunlight penetrates to the surface, but appears kind of an orange due to the clouds absorbing blue light. We do see atmospheric features. These are these vortices that are. And by the way, this is actually a very common thing that happens throughout the solar system, including here on Earth. There are what they call polar vortexes, that the winds whip around in a vortex, which is just a circulating wind. And like I said, that happens all over the solar system. Let's see, there's one that's a really strange looking one. It's kind of hexagon shape. I think it's on Jupiter, actually, now that I think about it. Anyhow, we'll get to that a little bit later. All right, so the motion is driven by the heating near the equator, and as the gas expands, then you get this motion that leads to these vortices. All right, so that's enough of that. Let's see, atmospheric pressure, as I mentioned before, it's actually not quite 100 times. It's closer to 90 times the pressure on Venus than it is on Earth. The lower the atmospheric pressure, is very hot with a temperature of 750 Kelvin at the surface. And so this is one of the things that we will often talk about, is that it's actually hot enough to melt lead on the surface of Venus. We have had spacecraft land there. They were called the Venera program. There's going to be some pictures from Venera in just a minute. They did not last very long. It was the former Soviet Union that sent these spacecraft, and they had been sending these spacecraft since the 1960s. There were multiple Venera projects. They call like Venera 1, 2, 3. I forget which one it was that actually landed in the 1970s. They finally landed one, and it didn't last very long. All right, Venus has 300,000 times more atmospheric carbon dioxide than Earth, which causes an enormous greenhouse. I mean, strong is that's too weak of a word to describe the greenhouse effect on Venus. It's actually what we would call a runaway greenhouse effect. The effect is so strong that Venus's surface is so because of this incredible thick atmosphere, and all the heat that ever hits Venus pretty much stays on Venus. That's the idea of this runaway greenhouse effect. It's hot enough, as I said before, to melt lead. Lead could not exist as a solid on the planet Venus. All right. Blah, blah. High temperature and density of the atmosphere created the high Venusian atmospheric pressure of Venus. So the Venus Express was, if I remember correctly, Venus Express was launched by I think that was the European Space Agency, and it detected hydrogen gas escaping from Venus into space, which is so this is photodissociation. In other words, if there was any water molecules in the upper atmosphere of Venus, the light photons would separate the hydrogen from the oxygen, and the hydrogen would escape out into space. Venus may have had oceans